Okay, so welcome again to lecture 5 of this course, Fundamentals of Solar Photovoltaics and Technologies. So today we will talk about solar radiation. So before we do that, let's briefly recap as to what we did in last few lectures. So this whole course has originated from the need to understand solar photovoltaics, which is mainly because of making a switch from fossil fuel based energy to renewable energy. So the big question in front of us is that while our energy needs will go up, they are likely to go up as the population increases and as we become more prosperous. How can we meet our energy needs while curtailing the GHG emissions at the same time, which means that we must switch to renewable and non-fossil sources of energy for energy generation. And among many sources that are available to us, solar energy is one of the most abundant and ubiquitous source of energy. Solar energy can be converted into electricity directly using a method called as solar photovoltaic effect or photovoltaic effect. So basically we started learning about solar radiation. Solar radiation basically comes from the sun, so it is a measure of the energy that is intercepted by earth after it is being emitted by the sun, and earth being much smaller than the sun, we intercept only a very tiny amount of energy. So the mean extraterrestrial irradiance, that is normal, that is available on the outer fringes of the earth, normal to the solar beam. So if this is your sun and is coming like this, and this is your earth, so basically you can say a disk of area pi r square, whatever is received on it is equivalent to 1.35 kilowatts per meter square. And of course, if you consider it over a whole earth, considering that it is a sphere, then you have to divide it by 4, because the area of surface area of sphere is 4 pi r square. Now as the radiation moves from the outer atmosphere, outer fringes of the atmosphere to the surface, it undergoes variety of interactions with the atmospheric content, and this results in significant amount of losses, and what we get actually on the surface is dependent upon many of these atmospheric factors. So what we are interested is in to determine the amount of solar energy that we receive at a given location at a given time of the year. So we need to consider geographic factors, we need to consider time factors, and we also need to consider the atmospheric factors in finally determining the amount of radiation that is available at a given location in the world. So first of these topics is solar constant. Solar constant basically is a measure of solar radiation intensity that is incident on an object, and this basically derives from Stefan-Boltzmann equation. So whatever is radiant intensity from sun, if you multiply that by the square of radius of sun divided by the square of the distance of earth from sun, that will give you the radiation intensity that is available on the earth. So this is H naught in watt per meter square, it is equal to H sun, whatever is emitted from sun, multiplied by R sun square divided by D square, and this value turns out to be approximately 13.66 to be precise, but roughly it is written as 1.35 kilowatts per meter square, but for the sake of preciseness you can say it is 1366 watt per meter square, that is the mean solar irradiance, and you can see that it varies from planet to planet. So you can see that Mercury and Venus receive far more radiation as compared to Earth, and Earth receives far more radiation as compared to other planets which are farther than Earth. So it's basically a very strong function of its own size and the distance, the size of the sun and the distance from the sun, because all of these things are smaller than sun. So naturally the distance between these sun and the receptor plays a very important role in determining the final amount. So this is something which is also dependent upon the day of the year. So the radiant power density that is available outside the Earth's atmosphere is approximated as or it is empirically determined as HSC, that is solar constant, multiplied by 1 plus 0.033 into cos of 360 n divided by 365, and this n is nothing but number of the day of the year, and HSC is the solar constant, which is 1367 watt per meter square, or some people also write it as 1350 watt per meter square. And the variation, that is, you can see this factor of 0.033, it tells you that there is a variation of 3.3% over the year, and this is basically because of orbital ellipticity of the Earth, because Earth is, there is ellipticity in Earth's orbit. As a result, there is a little bit of variation, but for the sake of most calculations we take it as 1367 watt per meter square. So, the solar radiation that is incident on Earth, so outside Earth's atmosphere we get fairly constant solar radiation, which is a very constant value, but by the time it reaches Earth's surface it undergoes variety of interactions. So, it depends upon atmospheric conditions, because the contents of the atmosphere affect the absorption and scattering of radiation. This is affected by presence of clouds or water vapor that could be present in the atmosphere. It is also dependent upon the presence of gases such as carbon dioxide, ozone, and many other gases, methane, etc., that could be present in the atmosphere, or nitrous oxide. It is also dependent upon the presence of airborne particles such as pollutants as well as aerosols. So, presence of all these gases, molecules, water vapor, pollutants, aerosols, etc., it affects the amount of radiation that is received on the surface. It is also affected by the specific location, that is the latitude, and also time and day of the year. And the losses that occur by the time the radiation reaches the Earth's surface, it is mainly because of absorption and scattering or reflection, you can say. So, here in this plot you can see that the spectral radiance gets maximized in the visible region. So, watt per meter square intensity is highest in the visible region, and you can model this spectra at the top of the atmosphere using a black body spectra of 5250 degrees centigrade, but this gets reduced in intensity quite a lot once you measure it at the sea level. So, you can see that the red, the region in the red shows a significant reduction in the radiant intensity, and this is mainly because of atmospheric losses. In addition, we can also see that there are absorption bands for certain molecules such as oxygen or water or carbon dioxide. There are many other bands that could be present, for example, methane could be there, ozone could be there. So, all these ozone, you can see on the far left, is far more active in the UV region than in the other regions. So, all these absorption bands are because of trapping of this intensity within the atmosphere before it reaches the Earth. So, there is a significant reduction in the radiant intensity when it reaches the Earth. So, the losses in solar radiation that occur because of various conditions, and this can be quantified or represented in the form of a plot. So, let us say this is time in hours, and here we have let us say the solar irradiance, which is also reflected in output of PV panel. So, if you look, for example, from AM to start of the day until the end of the day, on a clear day you might see a profile like that. Okay. So, this is for a clear day when there are little atmospheric losses, when there is less cloud cover, etc. But if you have an overcast day, so this is for a when you have clouds etc. present in the atmosphere. So, the amount of irradiance which is received on surface will be significantly lower on a cloudy day as compared to on a clear day for roughly the same time in the year, let us say. So, there is a significant loss in the solar radiation that could be caused by the presence of atmospheric conditions, and this is a very important factor in affecting the performance of solar PV panels or any solar device where amount of radiation intensity is an important factor. So, this also brings us to the concept of what we call as how much of radiation is available directly. So, direct radiation and also indirect radiation. Okay. So, basically, I have managed to draw it on top of the text, but nevertheless. So, direct radiation basically is a component of radiation that reaches Earth's surface in line with the sun, that is the shortest path that is taken without a change of direction. So, if you have this as Earth and this as sun, let us say, and if it is reaching at this point, this is the shortest path. Okay. So, this will be your directly in line with this in line of sight. So, this is the component which is called as direct radiation, the one that travels through the shortest path without a change of direction. Second component is called as indirect radiation or diffuse radiation, and this is a scattered component which we receive at Earth's surface from all parts of the sky's hemisphere. So, basically if this is the object which is kept here, let us say this is where we have our solar panel, then that radiation will be the one which is from, you can say like this, it is coming from all the sides, and this is what is the diffuse radiation that we call it. And this diffuse radiation, this direct radiation goes down, it decreases on a cloudy day, and this is larger of the two. On a cloudy or overcast day. So, essentially this is what we call as diffuse radiation, and this will be your direct component. And the global radiation, we normally define radiation as a global radiation when we conduct the measurement, because on any given day you will have both the components present. So, you need to count for both of them. So, the global radiation is basically sum of both of them, that is direct plus indirect. Okay. So, to quantify the effect of loss of incident radiation by variety of these components, we use a quantity called as air mass. And air mass, because sun changes its position throughout the day, the conditions also change throughout the day. So, we need to average it out for a solar panel. So, air mass is a measure of path length that is taken by the incident light through the atmosphere, which is normalized with respect to the shortest possible path length when sun is at zenith. So, of course, let us say this is your surface, and sun could be at different places. Okay. So, you can have in the noon, the sun could be in this position, and at some other time the sun could be present at this position. Okay. And this is where we have our solar panel, let us say. So, we have one line of sight which is this and another line of sight which is this. So, naturally if you say this is x and this is y, then you can see that y is longer than x, and this angle between the two is called as theta z, and this position when sun is right on top is called as zenith position. When sun is at the zenith, that is right on top of the earth, or that is the noon time, right, the solar noon time. So, we can approximate this as, let us say we have a sun, we have sun falling on a object, let us say this is the object of height, let us say h. So, this is our object and this is of height h, and it is depending upon where the sun's position is, the shadow length will be, this will be your shadow length, let us say s. In such a case, we can define air mass as 1 plus s over h square to the power 0.5, and this is nothing but 1 over cos theta z, where theta z is the zenith angle, that is the angle between the line of sight of sun when it is not at zenith with respect to when sun is at the zenith. So, this air mass index is a very important measure of how do we quantify the effect of losses on solar radiation. So, there are multiple ways of analyzing this AM, we call it AM in general, and you will see solar radiation for practical purposes. We always say solar radiation as, for most locations we say AM 1.5. So, when you come across this term AM 1.5, you should not be surprised. It is coming from certain reasoning, and the reasoning is there are certain terms which are associated. For example, you can have AM 0, you can have AM 1, AM 1.5. What is the meaning of these digits? AM 0 means you are measuring when you are outside the Earth's atmosphere, which means no losses are taking place. AM 1 is the meaning when sun is at the zenith, and AM 1.5 will mean it is an average that reflects the solar spectrum throughout the day as it moves from east to the west. When it is at the east, the beam is nearly horizontal. When it is in the west, the beam is again nearly horizontal, because sun is moving from, so let us say this is your east, this is your west, and sun is moving like this, right. So, it is going from very long, traveling throughout the day from east to west, and that leads to change in the path length of sunlight as it goes from east to west on the object. So, we need to average it out. So, AM 1.5 for generally places like India reflects the average of the solar spectrum that we receive throughout the day. So, let us define these values. First is AM 0. AM 0 means 0 atmosphere, that means the spectrum is outside the atmosphere, and this is generally considered when we do not want to consider the atmospheric losses, and this is mainly for outer space applications such as for satellites. So, this we do not use for Earth. AM 1 is the one which is AM 1 you will get when theta cos theta z is equal to 1, which means theta will be equal to 0 degree. Okay. So, we are in the range of 1 to 1.1 for angles from 0 to 20, roughly 25 degree, and this is applicable for equatorial or tropical regions. So, this means that the spectrum that travels through the atmosphere to the sea level with the sun directly overhead is referred as AM1. So, a spectrum after traveling through the atmosphere to sea level with the sun directly overhead is referred to as AM1. This is true for equatorial and tropical regions. So, right at the equator. Okay. India is above the equator. So, we are in the northern hemisphere. If you consider for AM 1.5, then this represents mid latitude spectrum, and this is where we typically are for most countries in the northern hemisphere, except the ones which are very close to the poles. So, AM 1.5 represents the mid latitude spectrum at about 48.2 degree, and then AM 2 to 3, which means angles of about 60 degree to 70 degree. This is useful for high latitudes or temperate latitudes. And then AM 38 is something which is very, very close to horizon. So, these are the values which we generally consider for practical applications depending upon where we are. And this value of AM 1 or AM 1.5 or 2 to 3 is very useful in quantifying the effect of or averaging out the solar spectrum that you get on a given location. So, this picture, which is taken from NREL website, it tells you that AM 0, of course, outer atmosphere will give you without atmospheric losses very high irradiance, reaching about 2 plus watt per meter square per nanometer in the visible range. If you look at AM 1.5 direct is the green one. You can see it is significantly lower as compared to the outer atmosphere, the one that is available at AM 0 in the outer fringes. And if you consider direct and indirect both, then we get the blue spectrum, which is a little bit higher than the direct spectrum, and again it is lower than the AM 0, but this is the spectra that we get on an average for a location that is corresponding to AM 1.5. This is a plot of average daily radiation that, of course, it varies throughout the day, throughout the year, and also every day there are variations, but there are plots of average daily global radiation and average daily diffuse radiation for India, which have been compiled by Sukhatme and Nayak in this book Solar Energy. So, we can see that if you look at plots from January to February to March and so on and so forth, you can see that the radiations maximize around summer time. So, this is the summer time, May, June, when radiations in the North India tend to maximize, but you can see in the South India, in Kerala, etc., they decrease. So, in Kerala the maxima occurs around April or March. So, these plots give you a good idea about at which location, at what time of the year the radiation will be maximum. So, you can see for northwestern India, the better months are May and June, whereas for some place like Kerala, March, April, or maybe February, March, January, February, March, April are better. January will be a very bad time for North India, because in North India there is a lot of smog or fog because of winter, and there is a lot of moisture in the atmosphere. As a result, the radiations decrease significantly in the month of January. Similarly, in the North India, northern part, because of winter in winter months, because of shorter day and also more fog and smog, in the November, December, January time, or even February, up to February, the radiation is lower, whereas in southern India the pattern is southern, or coastal India the patterns are different. You can see the daily diffuse radiation, which is because of ambient. You can see that diffuse radiation is maximum around the monsoon time. You can see that around the monsoon time, starting from southern India, you can see the numbers are on higher side in the monsoon season because of atmospheric contents being much higher. So, this can also help you calculate the differences in global and diffuse to determine the direct radiation, at what radiation, in what month, at what location, how the radiation varies. Lastly, so to determine the intensity, not only we need information about the losses in the atmosphere, but we also need to learn about the solar time, because remember our time zones are defined with respect to Greenwich Mean Time. Greenwich Mean Time is in the UK, in London, near London. So India falls in time zone of 5:30 hours ahead of Greenwich, but whole of India is very vast. If you go to western part of India, the actual noon may be different as compared to what is Indian noon. So that is why we need to make corrections in the time factors to determine appropriate solar times. Solar times are not exactly similar to the times that we see in our watches, because sun is at zenith at different times in different places. So for example, in eastern part of India, the sun rises much earlier than in western part. Similarly, it sets much later in the western part as compared to the eastern part. So there are variations in the local solar time that we need to account for. So for this we need information of geographical locations such as longitude and latitude. So we can see this is the map of the earth, this is your North Pole, this is where we have, so somewhere here we will have South Pole, and lambda is longitude and phi is latitude. So here we can see that this line, the vertical line, is the line of constant longitude, okay, and this horizontal circle would be line of constant latitude, okay. And so these coordinates, so for a given position you will have a given phi lambda. So this tells you the address of that particular in terms of particular place in terms of coordinates. So for Greenwich Mean Time, for Greenwich in UK, we take lambda to be equal to 0, okay, and earth rotates 360 degree over 24 hour. So 360 divided by 24, that will be equal to 15. So here basically you can say every hour it will be 15 degree rotation, okay. So 15 degree per hour. So we can see that India is 5 hour 30 GMT plus 5 hour 30, which means we can convert this time into degrees. So many degrees we are on the right of Greenwich, okay. Similarly, if you go back to a position in America, that will be on the other side. So that is how you determine the coordinates and fix them with respect to UK Greenwich time and then make time corrections. So basically there are few things we need to know. First is the local standard time meridian, LSTM, which is in degrees, which in degrees is 15 degrees, because there is a rotation of 360 degree every 24 hour, multiplied by delta T LT minus GMT. LT is the local time and GMT is the Greenwich Mean Time, okay. So this difference, so 530 hours for India multiplied by 15 degrees will give you the LSTM, okay, local standard time meridian. Second important thing that we need to work out is equation of time. This needs to be calculated to correct for the eccentricity of Earth's orbit and axial tilt, and this is given as this equation 9.87 into sine of 2b minus 7.53 cos of b minus 1.5 sine b. This is the empirical equation, where b is 360 divided by 365 into n minus 81, where n is the number of the day of the year, okay. So the equation of time So, if you plot EOT versus number of days versus n, so it can go something like this. So, this kind of variation will occur as you calculate it. And remember, the LSTM we are calculating always with respect to GMT, which is the Greenwich Mean Time. Then second thing we need to know is what is the time correction factor, because although India is within 5:30 time zone, GMT plus 5:30 time zone, the time in Kolkata and time in Jaipur may not be same. So, to factor in the variation of the local solar time within a given time zone, because of vastness of the country, and this results in longitude variation, this is because of longitude variations within the same time zone, we need to correct for that also. So, time correction is nothing but 4 multiplied by longitude minus LSTM. So, the actual longitude of the particular place minus LSTM plus equation of time, and the factor of 4 is arising mainly because for every hour it is 15 degrees. So, for every 4 minutes it is 1 degree, right. So, local solar time can then be written as LT, the local time, plus time correction divided by 60, or you can write it as, if you just put everything together, LST, local solar time, is equal to local time, whatever the local time is, plus equation of time, plus or minus, depends upon whether you are on the left of Greenwich or right of the Greenwich, you are in east or west. So, plus or minus 4 into lambda SL minus lambda SS minus daylight saving. So, if you have daylight saving, so this will be local and this will be standard. Okay. So, standard with respect to whatever with respect to Greenwich is. So, let us do simple calculation. For Mumbai, let us say this is your latitude and longitude. So, this will be your longitude lambda and this will be phi. Okay. Let us say it is 1st of July and time is 14:30 hours, and Indian standard lambda is 82.5 degree of east, which is fine because we are GMT plus 5:30 hours. 5:30 will mean 75 plus 7.5, which is nothing but 82.5 degree east, right. So, Indian standard longitude will be 82.5 degree east. So, equation of time I can work out using this equation for the day which is 1st July. 1st July we can calculate what is the value of n, and using that we can calculate what is equation of time. It comes to minus 4 minutes. Then we can calculate what is local solar time. Local solar time will be local time plus equation of time plus or minus lambda SL minus lambda SS minus daylight saving. Okay. So, here India does not have any daylight saving, so we can ignore this part. Local time is 14:30 hours, India is in east, so we have minus here, minus 4 multiplied by lambda SL, which is the standard local thing, and minus 72 degree 51 minutes, we can convert it to 72.85. So, actually this should have been plus and this should have been 72.85 minus 82.5, because this is the standard one and this is the actual one, plus minus of 4 minutes, that is equation of time. And if you just do the mathematics, you will get local solar time of 13 hour 47 minute, which is good many minutes. You can see it's behind by more than 40 minutes. So, you can see that in the western part of India, now you can see the local solar time in western part of India is some hour behind or some minutes behind as compared to standard time that is taken as noon. So, standard noon at 12 at the standard location in India will not mean noon in Mumbai, it will be different. And finally, coming to another angle which is called as hour angle, which is the local solar time minus 12 into 15, it is an angular measure of time. So, basically by this we are converting the local solar time into angles by which the sun moves across the sky. So, of course, at solar noon omega will be equal to 0 because LST will be 12, and if the hour angle is negative, then if it is AM time before noon time, then it is negative, and if it is PM, then it is positive. So, for 1 PM for example, it will be 15 degree, and for 11 AM it will be minus 15 degrees. So, this is the end of this lecture. If you want to go through the problems, I would strongly recommend you to go through the problems in this book, chapter 3 Solar Energy by SP Sukhatme and Nayak, and you will also get an assignment to go through some of these problems. So, in summary, we have looked at solar radiation, which tells us about the incident energy from sun on earth. It has the radiant energy from sun has a T to the power 4 dependence because of a Stephen-Boltzmann equation, and what we get on earth depends upon wavelength. There is a spectral dependence, that is wavelength dependence. There is also dependence on the atmosphere, what kind of losses that can occur, and we quantify these losses by the means of calculating air mass. And then to calculate the intensity, we also need to account for the time differences across various locations at a very local level. So, in the next class, we will look at some more details of solar radiation, especially in terms of geometry and how to determine them. Thank you.